Hey, it's great to be presenting this work at TQC this year. This is a joint project with Aleksander Kubica and Krysta Svore, and it ties together a number of different areas of fault tolerance and quantum error correction to address what we think is an important question. Essentially, what of the known ways to achieve fault tolerance in a scalable quantum computer, what is the cheapest? What costs the fewest resources and why? Probably the best known approach to build a scalable quantum computing system is based on the surface code. And if you look inside the workings of a surface code based quantum computer, you find that the logical operations that are performed, so the gates that need to be run on the quantum computer to implement the quantum algorithm, split naturally into two types. There are the Clifford operations, which are in some sense natural and relatively straightforward to implement in surface code. And then there are other non-Clifford operations. And of course, both of these are necessary. We can't get away with only Clifford operations. That would not be universal for fault-tolerant quantum computation. But so we need both of these. And at first glance, when you first see this, it may seem like this division into these two subclasses of operations is relatively arbitrary. But there are some hints at this being a little bit more fundamental than you might first think. You might think, for example, that it's really something specific for the surface code, or just the details that the community has found so far to implement fault-tolerant quantum computation with the surface code. But yes, they seem to go a little bit deeper, these results. A first hint at that is from the Easton and Knill theorem, which tells us that any quantum error correcting code that you have, the set of the set of transverse gates that code admits, which are the straightforward, direct, fault-tolerant gates that you can implement in the code, that set of gates cannot be universal, which tells us that any quantum computer based on any code, any specific code, will have some transverse gates which are not enough, and then in order to build a full fault-tolerant quantum computer, we'll have to have some other gates which are not transverse. So we know that the gates have to be somehow split up in a very general setting into two types at least. Moreover, Ravi and Koenig refined these results for the class of codes that you can describe as 2D local. So these are codes where you can implement the check operators using geometrically local stabilizers in a 2D layout. And then in this setting, they proved that the transverse gates not only are not universal, but in fact have to be Clifford. So this division of operations into Clifford and non-Clifford seems somewhat fundamental, provided that our quantum computer is based on 2D codes, which are non-Clifford. If you then take this surface code type quantum computer and you actually calculate how many resources would be required to implement some specific real-world large-scale algorithm, then you often find that the resources that are assigned to handle these two types of operations are very unbalanced, and in fact that the non-Clifford operations can often dominate the overall footprint of the quantum computer. So clearly this motivates us to look at these non-Clifford operations a little bit more closely and to think about if they can be improved. So what are the ways that one can implement non-Clifford operations in a fault-tolerant way? Well, there are a range of approaches that have been found over time. The earliest was the approach that was introduced in the early fault tolerance proofs, and a number of different approaches have been found since then. But if you look at this geometrically local 2D scenario, then it turns out that the only approach that is known, which is scalable, so has a threshold in this setting of two-dimensional local codes, The only approach is state distillation. So in this project, we wanted to take this kind of status quo approach of building a quantum computer with 2D codes using state distillation to implement the non-Clifford gates and compare it with an alternative. And of course, we want the minimum. We want to have. We know that 2D local the 2D local setting is not enough to do that, at least with the known approaches. So we wanted to do something which was a little bit more general than 2D local, but not too much. And of course, the next best thing, the next easiest thing that you could imagine is 3D local codes. And that opens up just one other of these broad approaches, which is that of code switching. So essentially in this project, we take the most basic thing that you can think of in terms of producing a non-Clifford operation, which is to produce a T state. It's just a 1 qubit non-Clifford state, that non-stabilizer state. And we compare these two approaches. So we compare state distillation, which was introduced, by the way, by Knill in 2004, and closely thereafter was also potentially independently introduced by Bravi and Kitaev. I don't know the exact history of that. And code switching, which is the other approach that we're going to compare with, it was introduced by Paesnick and Reichardt in 2013, and then was generalized in a very specific setting, and then was generalized by Hector Baumann to the case of 3D color codes, which is really what we're going to focus on here. So in the rest of the talk, I'm first going to specify and make a little bit more specific our assumptions. Then I'm going to outline what can be done with 2D hardware. So essentially how the Clifford part of the quantum computer, 2D quantum computer would work. Then we're going to go into how distillation would work in that setting. And then we will look at code switching and in 3 dimensions. And finally, we will collect together these different parts and we'll compare the two approaches and conclude. So our assumptions are really just about the operations that are allowed in 2 and 3 dimensions and the noise which is associated with that. So in the 2D case, we imagine a grid of qubits laid out like this. Each little dot is a qubit, and we allow for arbitrary single qubit quantum operations. So preparations, measurements, gates, etc. And pairs of qubits can be involved in quantum operations, but only if they're nearby. So if they, for example, fit inside this little window, which we can slide around, then that's fine. Then you can apply an operation between that pair. But if they're too far apart, you cannot. And the noise model is the standard circuit noise model. So every operation will fail with probability P. And just to give an example of what that might mean, if you were to prepare a single qubit in 0 state, then with probability P, it will actually be prepared in the orthogonal state, the 1 state. Similarly, if you were to apply a C0 gate between a pair of qubits, then with probability P, immediately after that C0 gate, there would be a random Pauli operator applied to the support of the C0. So that's 2 dimensions. 3 dimensions is really the same, or the direct generalization of this is just that this little window, which slides around and tells you where your 2 qubit gates can act, is now like a little cube rather than a square. So what can be done in 2 dimensions? Well, the first thing that we can do, of course, is to build surface codes. And in order to do that, we can imagine tiling the plane with, just for visual purposes, with these alternating colored squares. And then we can break up those squares into little patches, where each patch encodes a single logical qubit in a surface code. So here we see this is a distance 5 surface code, and in fact a bunch of distance 5 surface codes tiling the plane. In this talk, however, we're actually going to focus on a close cousin of the surface code, which is the color code. And it starts out similarly. We tile the plane just for visual purposes, but now with hexagons rather than squares. And then break up these hexagons into little patches where each patch encodes a two-dimensional color code. In this case, we have a distance 5 2D color code shown. And the key idea here is that the information which is stored in each of these patches, each patch holds a logical qubit, is protected from noise. So if you grow the size of the patch, I mentioned this was distance d equals 5 here, but you can scale that distance d, and you can suppress the probability of an error acting on the logical information that you encode arbitrarily by just building the patches bigger and bigger. And this works provided that the threshold, provided that the probability of each single operation error is below some threshold value. But in the case of color and surface codes, these thresholds are actually relatively high and compare favorably against other quantum error correcting schemes. So something else that's really important with color codes, are very natural, is that each you can actually implement the full set of Clifford group unitaries on each individual logical qubit. And you do this transversely. For example, the Hadamard is implemented by separately addressing each of the data qubits in the code by a physical Hadamard, and this implements the Hadamard at the logical level. This is an example of a transverse gate, which I mentioned earlier, and you can see that these are fault tolerant naturally because they don't spread errors. We're addressing each individual qubit separately, and therefore some error on some region will not spread to other regions, and that's why these gates are fault tolerant. Something else that you can do with 2D color codes is that you can couple them together. So you can implement joint Pauli measurements between pairs of 2D color codes, provided that they share an edge. So this induces a kind of hexagonal lattice between logical qubits, and in each of those pairs connected by an edge in this logical lattice, you can measure a joint Pauli operator. Now together, this set of operations, so the single qubit Cliffords and the logical Pauli measurements between adjacent patches, generates the full Clifford group, and all of these operations are protected. Great, so in 2D we can implement all of the Clifford operations in a fault-tolerant protected way using, for example, the color codes. So how do we implement the non-Clifford gate in that setting? Well, we do it with distillation, as I mentioned before, and this is a very clever idea where you actually start with some small unprotected T state, so that can be produced, but it's going to be very noisy, and then you expand this from being in a very small encoded qubit to a larger one, which seems initially like a strange thing to do because now we are using many qubits to build this large patch of color code with this encoded state in it, which in principle is capable of protecting a very high fidelity encoded state, but this state is very noisy because we prepared it in a non-fault tolerant way. But the reason we do that is because the workhorse of the distillation protocol is in fact a Clifford circuit, which we know we can run on this patch or on these sets of patches using what I described above, the Clifford operations in 2D color codes, and this will output. It's a post-selected circuit, so it will output a much higher fidelity T state than you input. And you need to input a number of copies of T states here. It may still not be enough for the purpose of your large scale quantum computation, so you might need to iterate this a number of times to get the desired quality. But once you do have it, then you can use that T state to implement the T gate, the non-Clifford gate. Okay, so at a high level, that's how distillation works. It can, of course, be very costly. The first reason to see this is just the fact that it has this kind of hierarchy. You need to start with many inputs and you get fewer outputs, and you do this multiple potentially over multiple rounds, so that can end up with many inputs being needed at the start, which can be very expensive. Another reason that it's expensive is just, this is one operation we're talking about here, but the distillation circuit itself, the Clifford circuit, has many components. This is a laid out version of the circuit for a particular distillation scheme, the 15-to-1 scheme, and this is the circuit that we actually considered in this paper. And it's a very standard circuit, but it's very large. You can see that there's a large footprint, and this is just one round of distillation. You might need many, and so all of the resources here of all of these Clifford operations add up to give you quite a high cost to produce just one T state. And in this project, our goal was to, of course, assess this cost, the cost to produce a T state for a particular target output infidelity. And to do this, we had to do a number of things. First of all, since we're dealing with color codes rather than surface codes, a lot less is known and understood about how the color codes work. And so we put a considerable amount of effort into optimizing the two-dimensional color code, which involved optimizing stabilizer extraction circuits and building a fault-tolerant decoder for that setting. And once we had that, we were then able to simulate logical errors in the 15-to-1 distillation circuit. And that, once we had that part, then we were able to rapidly test many different distances or sequences of distances for a particular distillation scheme. So what I mean by that is to specify a distillation scheme, you need to say how many rounds of distillation there are here, big N, and what the distance of codes used at each round is, these little d's here. And we could just try many different combinations and find the cheapest, the least expensive one, which produces some target output fidelity Q out. And here I just plot what we found. It's so unsurprisingly, the qubit overhead is large, but also it increases whenever you increase the requirements of the quality of the output T state. And also it increases considerably if you decrease the quality of the qubits which are used. So if you essentially increase the noise in the underlying qubit hardware, which is this little p here. And in this project, we look at a range of different values of p, which is from 10 to the minus 3 to 10 to the minus 4, which is kind of the physically reasonable range, we would argue. Great, so we've seen how to implement a non-Clifford operation in 2D using state distillation. What about 3D? So in 3 dimensions, our approach is going to be based on the 3D color code, and that's really a direct generalization of the two-dimensional color code. Although, of course, by the name, you could guess that it's built instead of a 2D grid of qubits in a 3D grid of qubits. So in the three-dimensional color code, similar to the 2D color code, there are some transverse gates. Although the 2D color code had the full Clifford group, the 3D color code does not, but crucially has the T gate transverse. So that means that if you're able to produce and use the 3D color code, then you would be able to implement the T gate fault tolerantly in this very direct way by just applying a transverse T operation to each data qubit in the code. But because you don't have the single qubit Clifford group, this is not enough for a universal fault tolerant quantum computer. So the three-dimensional color code is a stabilizer code, and that means that there are a set of local check operators which all have to be satisfied by the code. And an important generalization that you can make of this code is actually to ignore some of those check operators. So what that means is in the 3D color code, the standard 3D color code, we have some stabilizer group. And if we take just a subgroup of that, we'll have a smaller stabilizer group, and that in fact there exists a choice which defines the 3D gauge color code. We call that this, or you can call it the subsystem color code. And something that's pretty clear from the way that I described the definition is that if you have some state, which is a code state of the 3D color code, the stabilizer version, then because the gauge color code just has a sub stabilizer group of the stabilizer color code, then the state is automatically a state of the subsystem code too. So the 3D gauge color code is a generalization essentially of the stabilizer code. Moreover, if you have some state of the 3D gauge color code, that's not necessarily a state of the subsystem color code, but you can, in principle, measure the additional stabilizers which are not satisfied and apply some fix operation to ensure that they become satisfied, and that will allow you to move into the subsystem color code. So that starts to sound useful. It's allowing us to move from one version of the 3D color code to another. But really, at the end of the day, what we would like to do is to be able to put to move our information not from the 3D stabilizer color code to the 3D subsystem color code, but from the 3D stabilizer color code to the 2D stabilizer color code, where we have the full Clifford group and where we know how to do everything in this nice 2D fashion. Well, something that's kind of remarkable that was pointed out by Hector Baumann is that in fact there is another choice of the 3D subsystem color code where you can actually, so you can choose to measure some other set of additional stabilizer operators, which actually put you into two decoupled codes. One is precisely the 2D color code along the boundary, around the facet of this tetrahedron, and the other is some stabilizer state of the bulk. And so that process can be implemented by gauge fixing. And of course, since this, it's exactly the same story as going from the 3D stabilizer code to the subsystem code, since this is a particular gauge fixing of the 3D subsystem code, if you start in the 2D color code, provided you also have the bulk prepared in the correct stabilizer state, then you are automatically in a state of the subsystem code. And this allows us a pathway to move between the 3D stabilizer code and the 2D stabilizer code. So how can we use this to produce a non-Clifford state, the T state? Well, we use a 6-step protocol as shown here. There are a number of different ways to do this, of course, and we chose this one because we believe that it will perform the best of the various ways that we considered, but there could be modifications of this too. So the first step is we produce a pair of two-dimensional color codes in a Bell state. So then we take one half of that Bell state, the darker shaded one here, and prepare the bulk that I described before, so that the overall state of the system in step 2 is in fact a particular gauge fixing of the 3-dimensional gauge color code. So to go from step 2 to step 3, all we do is measure the gauge operators. Our goal is to transfer to the 3D stabilizer color code. So we need to measure those additional stabilizer operators and fix them. And of course that's going to be imperfect, so not all of them will be fixed, which is kind of represented by these residual loops here. After that, we're not exactly in the 3D stabilizer because of these errors. Sorry for the noise in the background. But we're pretty close. The residual errors should be small if we are below threshold and if everything is working well. So we're close enough that we can apply the the t transversely to the system, and it will, up to residual error, will implement the logical t gate. So we do that, and then afterwards we measure the entire 3D color code out, which initially might seem like a strange thing to go to all that work and then measure all the qubits out and everything is collapsed. But the reason, of course, is that we remember that we had this bell pair that we produced. So in fact, this will teleport the T gate to the other half of the bell pair. And at this point, we need the outcome of that measurement that we did of the 3D color code in order to know whether we have the T state or we have something orthogonal to the T state. And the real reason that we do this, the real reason that we produce do this protocol using a bell pair, is that this destructive measurement of the 3D color code puts us in a setting where we have much more information about the measurement outcomes than we would if we weren't doing a destructive measurement. And so we believe that that makes the job a lot easier, and therefore will result in better performance. Okay, so to simulate this, we implemented that full protocol end to end. Of course, that required many things to be specified, exactly how the gauge operators would be measured. We needed to develop decoders, and so we needed to develop a decoder for gauge fixing. We also needed to develop a decoder for the readout at the end of the protocol, or we needed to implement one. There were some that were known, and this required, of course, a lot of work, but in principle, it's possible by putting together pieces and generalizing a few things that were known in the literature. For example, at the time of this, that we were writing this, there was initially no known decoder for the 3D color code, and then there was, which was developed by Alex and Nicolas Delfosse, but it wasn't generalized for the specific case of the 3D color code with boundaries, so we had to generalize things a little bit. So you can imagine there were lots of pieces that had to be put together to build this simulation. But once we had it, then it's a relatively simple task to just run for a range of distances and a range of values of physical error rate, and then to extrapolate beyond the distances that we were able to explore in our relatively rudimentary simulation, we fit a simple standard form to the failure rate as a function of the underlying physical error rate and the code distance, and then we can use that fit in order to extrapolate. Something that I want to describe in a little bit of detail now is that we bounded what we wanted to do was bound the impact of anything being improved over our current simulation. So, for example, the interior needed to be prepared. We found a minimum depth circuit to do that, but there are many minimum depth circuits to prepare this state. Some of them will result in worse error propagation than others. And so in order to identify the potential impact of a new protocol for preparing the interior, we replaced that step with something which was ideal. So it was in fact a preparation where the noise was completely independent, no correlations, there were no circuits, and it was just 3 rounds of idle steps, which is the minimum amount of time that would be required, because each qubit is involved in 3 stabilizers, so we knew that at least 3 steps would be required to produce this state. Okay, so when you do that, the performance that you measure improves. We're not claiming that you could actually achieve this, but if you were to improve this particular part of preparing the interior, then we're confident that this is the most improvement that you could get by doing that. And probably you're not going to be able to do quite as well as that, because this is really kind of optimal. And we did that for all of the different steps. So for each step, we found we bounded what could be improved. And then finally, we put all of the pieces together and we compare the cost of code switching and state distillation for a variety of underlying values of physical error rate P. So let me first show you these two here. So the lines to focus on are the blue and the green. So the blue line is code switching and the green line is state distillation. It's the ones that those are the same lines we showed earlier for state distillation. In the first pair of panels here, you don't actually see a blue line because in fact this is above this value of P is above the threshold that we observed for code switching. So there in principle is an infinite number of resources required for code switching. The yellow curve is our bound whenever we include all of the optimal improvements for everything, for all different steps of distillation, or sorry, of code switching. And notice that the yellow line is slightly below the line for distillation, but not a whole lot. And also, we don't really believe that you could ever achieve, everything being absolutely optimal. So, so the results are not extremely optimistic for code switching, because really we see that code switching and code switching is more expensive than state distillation, and even if you made all of these improvements, then you wouldn't really drop the cost very much, not more than an order of magnitude in the range of error rates that we studied. So that's somewhat disappointing. But unfortunately, that's what we observed. Another thing that you can look at is the asymptotic behavior of both code switching and of distillation as the output error rate goes to 0. So in the case of code switching, since the T state is really just produced in a 3D color code, which is subject to noise during ongoing error correction as normal, we expect that the probability of failure of any state, including the T state, which is produced in the 3D color code, should go down exponentially with the code distance. So it should behave in this way. Alpha is some number below 1, and the probability of failure of the overall T state should scale like alpha to the D for some alpha. And we can simply invert that for D and note that since this is a 3D color code and the number of qubits scales like D cubed, then the space cost should behave as log 1 over Q out all to the power of 3. So that's a simple analysis for the code switching case. Distillation, there is a well-known argument that there's a parameter usually referred to as gamma, which is essentially the logarithm of the number of inputs to outputs for a distillation scheme, where the logarithm base is the order of error suppression of the distillation scheme. And then the space cost, so essentially the number of inputs to the first round of distillation, scales in the same way as for code switching, but with a different exponent. And in this case, the exponent will be gamma. I have replaced gamma by this number 2.46 here, which is the value of gamma for the 15-to-1 scheme that we analyze in this paper. And so it's clear here that in this asymptotic regime, code switching still does worse than distillation, just because this power is lower in the case of distillation. If you look at the space-time cost, these powers just have 1 added to them, so nothing surprising there too. Parameters. Okay, so our main conclusion is that code switching is at least not substantially cheaper than state distillation for the range of error rates that we looked at, which we would really hope it to be in order to justify building three-dimensional systems, which can be very difficult in practice. Our results are, because of this analysis that we did by replacing each step with an optimal version, but this comparison still holds even in that regime. This is slightly more just our opinion, but I personally don't believe that there are some other versions of code switching. I don't believe that they are likely to improve upon this. And really my reason for saying that is if you look at the other approaches to code switching, either they're very, very similar, at least in a topological sense, where you're replacing the color code by the surface code or something like that, or they actually require further constraints. So instead of implementing the 3D color code using a three-dimensional spatial lattice, you could, for example, use a just-in-time decoding scheme and implement it in 2D slices at a time, but that's constraining the system even further. And so to me, it seems very unlikely that that would require fewer or lower overall space-time cost. I would expect it to require much more because it's constrained, so it's going to perform worse. I would expect, but again, that's my opinion. Okay, I will end there without adding further conclusions. Thank you very much for your time.